Thanks, Daniela, and thank you for coming. So if we haven't met, I'm Nir, and I'm going to tell you about time lock puzzles from Randomized Encodings. And this is joint work with Shafi Goldwasser, Abhishek Jain, Or Panef, Vinod Vaikuntanathan, and Brent Waters. Okay. So let me start with the concept of time-released encryption that was introduced by May and further developed by Rivest-Shamir-Wagner. And this is basically Goldwasser-Micali meets Marty McFly and Doc Brown. Probabilistic encryption meets time travel. Okay? What we want to do here is encrypt to the future. Okay? We want to encrypt to the future. Okay, so this sounds pretty cool, but what do I really mean by encrypting to the future? So we know how to encrypt, but what we'd like to do is encrypt in a way so that everyone can open our encryption, but only after a certain amount of time that the encryptor specify, has elapsed. Okay, so other than cool, this also seems pretty useful. For example, you can try to use it in auctions in order to steal your bids, or in digital votings to steal votes. You can encrypt to the future your diary so that your secrets will only be revealed after you die, right? And there are many more very nice applications that you can find in the literature. Okay. So there are basically two approaches to go about this problem. One relies on trusted parties, and the other one, which I'm going to focus on today, doesn't assume any trusted parties and relies on this very nice notion of time lock puzzles. Okay. So let me tell you what time lock puzzles are. So the syntax is very similar to that of encryption. We have basically an encryption algorithm that generates a puzzle. It takes a message M and some time T, and it generates this puzzle. Why do we call it a puzzle? Because it's not exactly a cipher. Anyone can solve it. There's this public decryption algorithm, and you don't need any secret key. What you need is time. Okay? So if you have enough time, if you run for enough time, you can recover the message M from this puzzle. Okay. Now, the encryption is really important. We can do it very fast. Okay? Essentially independently of T. It's immediate. Now, what is the security requirement here? What do we really want here? So we don't want anyone to be able to open the message before time T has passed. So adversaries running in time significantly less than T should not be able to learn the message or even any information about the message. You can imagine it's semantically secure. But furthermore, we want this to even hold. If our adversaries are very resourceful, perhaps they have multiple cores, polynomially many, we still don't want them to gain any information about the message. And more generally, we're going to think about circuits. Our adversaries are going to be circuits that have arbitrary polynomial size in some security parameter that could potentially be larger than T. The number of the width could be larger than T, but their depth, their parallel time, is shorter than T. Okay? So this is the adversaries that we'll have in mind. And these are time lock puzzles. And if you have time lock puzzles, you can encrypt to the future. Okay. So let me tell you a little bit about existing constructions for these creatures. And actually, I'm not going to be able to tell you about constructions because we have only one. We have a single construction for this creature. It's a very elegant construction by Rivest-Shamir and Wagner. It's worth knowing if you haven't encountered it yet, so I'm actually going to tell you about it. We'll see how it looks and also get a better sense of this notion. Okay, so how do you encrypt to the future in their scheme? So the encryption algorithm takes the message and the time T, and it's going to generate an RSA number N, the product of two large primes, and also a random number R mod N. And now, in order to pad our message, what we're going to do is we're going to compute this R to the power of 2 to the T mod N. Okay? Now, if we generate these puzzles ourselves, and we know the factors, p and q of n, so we know the order of the multiplicative proof, phi of n, and we can actually do this very fast. We can first compute 2 to the t mod phi of n. This only requires roughly log t squarings, and this gives us all that we need in order to generate these puzzles. On the other hand, if you don't know p and q, if you only get n, computing phi of n is hard. In fact, it is as hard as factoring. But you can still do squarings modulo n of this r here, but it will take you t squarings. Okay? The question is whether you can do more than that. And you can conjecture that this thing is really inherently sequential. And indeed, the best we can do here, the best that we know, is really to assume that this thing as is really secure. It's inherently sequential. You cannot hope to parallelize this. We don't really have a reduction, okay, to factoring or even to RSA. Okay? But we have strong intuition. Okay. So this is the only construction that we have, and the question is why only one? Okay, can we come up? Yeah, Rachel, you had a question?
I have one confusion about the functionality.
The functionality of time lock puzzles. Yeah.
I want my puzzle to be not solved in the next 20 years or 50 years until I die.
Okay.
Does that mean that...
Are you going to die in 50 years? In 15 years? I'm bored. Uh-huh. Okay, yeah, encrypt into 15 years, like...
T is 100 years. Does that mean that someone after I die, in order to open it, has to actually run 100 years?
Basically, yes. But, you can think about more sophisticated things, perhaps. I don't know, you can give some secret key to someone you trust. I don't know. But yes, basically, yes. Okay? You're going to put it in a lock for 100 years. You decide on the time. Okay, so back to our question. Why only one constructions? We want more candidates. Can we have more candidates? And can we actually come up with proofs of security, to more typical cryptographic assumptions like those that we're used to? And let's try to understand better the difficulty here. So what exactly is it that we're looking for? So first, we're looking for problems that are inherently sequential, also in the average case. Okay? And if you think about typical cryptographic problem, I don't know, a naive attempt, say, invert a one-way function on a range that has size related to t, then this won't really cut it because it's extremely parallelizable. Okay, so this is the first challenge, actually finding things that are hard to parallelize on the average case. But even if you have this, it's still not enough. It's really important that we have this ability to quickly come up with this puzzle together with the solution, so that we can encrypt whatever message that we want. Okay? So for example, even if we believe that, say, some iterated hash function, I don't know, SHA, is really inherently sequential, it's still not enough because we don't have any way of speeding it up. We don't have any trapdoor in this thing. We really need something like we had in the RSW construction, where we can compute it fast, say, given some trapdoor information. Okay? And these two properties are sort of elusive, kind of hard to come by, and it's really a question of where we should look for those things. And I'd like to point out that, typical cryptographic assumptions probably won't cut it. Okay? We need more here. And the thing is, if you look at that standard or typical cryptographic assumptions and our adversarial model, it doesn't really say anything about parallelism. It doesn't say anything about diff. All the adversaries fall into this pool of polynomial size. And taking to the extreme, it could be that we have crypto, we have one-way functions, perhaps even distinguishability obfuscation, and yet everything is parallelizable, okay, in a very strong sense. Okay, so of course that we don't believe that everything is parallelizable, Okay, but this is just to make the point that some assumption, okay, regarding non-parallelizability, okay, outside of the typical crypto that we know seems necessary. Okay, there's really a complexity theoretic barrier here. Okay, so let me tell you still at a very high level what we show. Okay? So what we essentially show is how you can, we give new constructions and actually a new approach to constructing time loop puzzles. We show how you can separate the crypto component to, a typical crypto component like we know and like. And as I said, we also need some complexity assumption and some minimal complexity assumption. Okay? And with these two components, we'll construct new time loop puzzles. This is still at a very high level. I now need to tell you what is the crypto component, okay? What is this assumption, and what is the construction? Okay. Yes.
Essential, you think, or could you?
Yes. I'll say a word at the end. The crypto is essential. You need actually crypto. Okay. At least one-way functions. Yes, Benny?
The other question is, so P not equal to NC is necessary? It's not immediate to me.
That what?
That you need really to assume that P is not equal to NC, for example. Or was it just an example in your
Well, time loop puzzles already imply some sort of non-parallelism, right? If you can parallelize everything.
I'm not sure what's the, is it polynomial time? Like solving the puzzle is in polynomial time eventually?
Yes. So we're thinking about polynomial time. Yes. Everything is polynomial time. We're thinking about precise notion of security. Okay, good. Okay, I'm going to start with the crypto component, and this is randomized encoding, something that Benny talked about quite elaborately in the boot camp. But let me remind you what those are. So in a randomized encoding scheme, we have two algorithms, an encoder and a decoder. And we would like to take a computation, say given by some Turing machine, and an input, and encode it in some way. It's a randomized encoding. Okay? And we want it to have the following properties. So first, this encoded computation can be decoded by this public decoder. Again, you don't need any additional information for that. And the decoder can retrieve the result of the computation. Okay. Now, what is crucial here is that we want the encoder to be significantly simpler than the computation itself. Okay, and we'll get to this point in a bit. Decoding, on the other hand, can be as complex as the computation itself. Okay, what do we want in terms of security? So in terms of security, we basically want that this encoding doesn't reveal anything about the computation except for the final result. Okay, you can't send this machine the input in the clear. It really has to reveal nothing but the output. In other words, you can simulate this encoding just from the output and let's say the time of the computation. Okay, this is also something that leaks. And for the purpose of this talk, I don't really care if this simulator is efficient or not efficient. Both would do. Okay, so now to simple. What does simple mean here? And simple could have different meanings, different interpretations. So Benny talked mostly about the encoding being shallow or local. Okay, but there are also other complexity measures that you can think about. And in this talk, I'm going to focus on a very specific one. I'm going to require that the encoding is very fast. Okay? And with these fast randomized encodings, we're going to get full-fledged time loop puzzles. But let me already say here that even if you start from weaker notion of time loop puzzle, of randomized encodings, you still get some time loop puzzles, weaker notions of time loop puzzles, but which still seem meaningful. Okay. But again, today we're going to focus on this thing. Okay. So what are fast randomized encoding, also known as succinct randomized encoding? As is, just the encoding is very fast. The time to encode is significantly shorter, say independent of the time of the computation. Decoding takes the same time. Functionality is, security as before, simply simulation. Do we have this thing? Well, can we construct it? So at this point, at least, we only know how to construct it from indistinguishability obfuscation. It's a pretty strong object. But as far as we know, it could be weaker. I'm going to touch this point again at the end. OK, so this is the crypto component. And in fact, before I tell you what is the complexity assumption, I'm going to jump right ahead to the construction. Because it's really simple, and actually it's not going to depend on the assumption itself. Okay? So let me tell you what it is, and then we'll develop some intuition about what the assumption should be. What is the complexity assumption?
So
okay.
Just,
yes.
On the previous slide, so this construction of obfuscation, just to get more familiar, what's the intuition? What would be the simplest construction from obfuscation?
Take a gate garbler for your garble circuit and obfuscate it. Just one line. Think about it. It's more than that. You just ask for a sentence. OK, so I want to describe the construction, the new time lock puzzle. The first thing we need to do is say, what is this encryption algorithm? And what is it going to be? Well, we're simply going to encode some computation using the Succinct randomized encoding and output this encoding. And what is this computation that we're going to encode? Well, in fact, it could be any long computation that has a very specific property. For example, we can think about a computation that makes t dummy steps absolutely nothing for t timestamps. And then at the end, it's going to output the message m. OK? So this is basically our time lock puzzle. Simple, no? Okay, a randomized encoding of this computation. Good. Notice that this is very fast, of course. The randomized encoding is fast. Exactly what we need. How do you solve the puzzle? Well, you just run the decoder for the randomized encoding. Right? We know the decoder can retrieve the output. Good. OK. This can be done in time t, which is OK. OK, so clearly has the functionality that we need. But let's try to get some intuition on why this thing is really secure. Why does it really give us what we need? Why can we expect it to give us what we want? OK, so remember that our randomized encoding, our puzzle here. Okay,
which machine, which computation do you do the randomized encoding to?
It's a computation that does nothing for t steps. OK, can ignore the input for every input. It's very lazy. And then at the end, it outputs the message m. OK, good. Now, in particular, this encoded computation is not supposed to reveal, by the security of the randomized encoding, anything but the output, but the message m. So it should be indistinguishable from any other encoded computation, right? As long as this other computation also outputs m at the end and, say, has the same number of steps. Okay? Now, well, we know that this computation really does nothing. Okay, and at the end, outputs m. As far as we know, this other computation could be something arbitrary. In particular, it could solve an inherently sequential problem. I don't know, some iterated hash, or any other thing that you might believe to be non-parallelizable. Okay? The adversary cannot tell. As long as these two, at the end, output the same message m, it cannot tell. Okay? So with this intuition in mind, we can really start thinking what should be the complexity assumption that we need. Because there seems to be a very nice universality property here. We don't really care that anything specific is inherently sequential. All that we care is that there's some inherently sequential computations in the world, and then we can plug them here. Okay, so let me now, yes.
A computation that gives m as a result.
Yes. Okay, so I'm going to wrap this whatever non-parallelizable computation, okay, just output m at the end. The randomized encoding sort of weld them together. This is the, sorry?
At the end, the m is independent of the input.
The m is independent of everything, yes.
Ignoring xt.
Yes. Good. Okay. now with this intuition in mind, we can really define what is our assumption, say what is our assumption. And our assumption is essentially that not everything is parallelizable. Okay? There are computations that cannot be parallelized. A little more formally, for any polynomial time function and say constant delta smaller than 1, we want a language that on one hand you can decide it in time t, even sequentially, okay? But you cannot parallelize it. Okay? So circuits that have depth significantly less than t, say t to the delta, will fail to decide it.
This is worst case or average case?
Good. So first comment, Evgeny, this is worst case. All that we care is that every circuit fails for some input. Okay. Another thing is that this is necessary. Really, if you think about it, time lock puzzles imply non-parallelizing languages, even in the average case. And the third thing is that this is really something that we widely believe. Okay, we don't believe that everything is parallelizable. Okay, it's a natural generalization of the assumption that P is not equal to NC. Yes, Juan.
I don't know if you mentioned this at the beginning, but Moni and Dambonnet have this generalized Blum-Blum-Shab assumption.
That under which you can, so the Blum-Blum-Shab is really similar to the...
You put the generalized, and there were follow-ups.
Maybe you can tell me about this at the end.
There's also a complex assumption, however strong.
So is it's a different assumption than the RSW that also gives you time lock puzzles?
Is Moni there?
Okay, maybe...
It's not inherently different.
It's not inherently different. Okay, you can tell me at the end. Thanks. Okay. So now let us restate the main result. Basically, the crypto components, succinct randomized encoding, and the complexity theoretic assumption, non-parallelizing languages, imply time lock puzzles. Okay, and I can say 2 words about the proof, just to get even a better sense of what's going on. It really follows the intuition that we had. We want to show that if we have a shallow circuit that can break our time lock puzzle, right? Let's say, for simplicity, really recover the message m for some random message m in time significantly, in depth significantly less than t. What we'd like to do is sort of a worst case to average case reduction. What we'd like to do is show that we can construct from this guy a decider that decides some non-parallelizing language L in the worst case. Okay? And how is it going to work? Well, we're simply going to run, the reduction is simply going to run this decider on some encoded computation. And what does this computation do? It takes the instance we want to decide. It decides the instance. This is something that we know we can do in sequential time, t. And if indeed the instance is in the language, it will output a random message. Otherwise, it won't output anything. Okay. Now at this point, we know that this guy would produce some message, and we're going to say that this instance psi is in the language only if it really got our random message, the encoded message. Okay? And why does this work? Oh, so first, again, note that this guy is shallow. We know that this guy is fast, or this entire thing is really shallow like we want. So it really breaks the non-parallelism. And the intuition is really going back to the picture that we just had. Okay? If really the instance is in the language, then we know that this encoded computation here is really indistinguishable from the other puzzles, because it will output m at the end. This is in the language, so m will be outputted. You cannot distinguish them. We know that in this case, the shallow circuit recovers m, so it will also recover m in this case. Okay. When psi is not in the language, then we know that this guy at the end will output nothing, right? So this encoded computation is really indistinguishable from a computation that has no information at all about m. Just outputs nothing at the end. So in particular, from this thing, you cannot recover the message m. Okay. So this is the idea. This is really sort of an average case to worst case reduction using randomized encodings. Okay. And I think that this sort of universality property here that you really get from the randomized encoding is sort of nice. Okay.
Wait,
Yes.
I'm not sure I really buy that because
Good.
this reject symbol is really kind of special. So you might have an adversary who's like, okay.
Take something arbitrary. You choose.
Okay, so then you
Just not the message M.
prime.
Yes.
Yes. Two questions. So what about the size of the Turing machine that you're going to obfuscate? Like,
So the size is small, right? It's basically a fixed Turing machine.
the security parameter, maybe very slowly, but just to make sure that maybe there is...
Things will grow here with the security parameter, but not with T.
Sure, okay, but so the size is not independent of the security parameter of this
No,
size?
no. Everything, yes. Everything depends on the security parameter.
So is there,
I'm pushing it under the carpet, but it is.
Is there an advantage to use I don't know, like a P-complete language instead of, like, you get universality for free because of the hiding property?
Right, we don't really care, right? We don't use any specific language in some sense.
So is it true that you really don't care? I mean, when
Yes,
you get...
yes.
Well, I believe that you don't care, but trying to say maybe like in terms of concrete security, like in this thing, if you use like a P-complete thing, I don't know, you get some advantage.
Okay, that's a question. I haven't thought about it. Yeah, you're saying instead of this lazy computation, use some very specific computation. I'm not sure, but need to think about it. Okay, so let me just mention that in the paper actually we have a couple of other results. So I already mentioned that you can get weaker time lock puzzles from weaker randomized encodings, okay, which in turn you can get from weaker assumptions. Okay, so even say the randomized encodings that we know how to construct from one-way functions, okay, in which the depth of the encoding is small, would still give you a meaningful time lock puzzle, where the depth of generating a puzzle is small, but still computing it requires sequential time. There's the caveat there, but yes, Shai.
What happens if you just relax the gap between the sequential?
It scales. So if you assume weaker non-parallelizability, you would get a weaker time lock puzzle. The construction doesn't change. This is something nice.
Suppose you only wanted the square root gap in between.
Right.
Could you get a construction from something weaker than IO?
Right. I don't know how to relax the cryptography. I would only know how to relax the complexity assumption.
So when you say weaker time lock puzzles, you mean time lock puzzles that to create them requires a lot of time?
Right. I mean that creating them may require a lot of time, but they can be parallelized. Actually, in this solution, there's another caveat. We'll get a very large puzzle. You can parallelize it, but it will be very large.
So garbled circuits give you...
Exactly. Good. And another point is you can actually try to apply this approach to different type of puzzles. So, for example, to proofs of work by Dork and Orr, you will have an equivalent of non-parallelizing language. You will have non-amortizing languages, but basically the same idea would work. And final thing, your question alone, we can show that time lock puzzles do require some crypto, at least one-way functions. It's not too surprising. It's interesting to see if it requires more. Okay, this strong notion of time lock puzzles. I don't know. Okay. Yes.
Very quickly. So there are these randomized encodings which don't require I/O, which are not quite succinct, for example, like online, offline, right? Offline.
Right.
Do they give you interesting thing, like if you just apply to Yao this online?
Yes. So we mentioned it. It will give you an interesting thing, but not the full. You would still get some gap between the person that generates the puzzle and the person that needs to solve the puzzle. Now the person that generates will be parallel, whereas this guy must be sequential.
For example, like can you do something? I don't know if it was known. Like I worked for 10 years. I expect to prove some cool result in 10 years. So I worked like on the side for 10 years to generate something. Then eventually I get the result, and now I can produce this.
Yes, you can also sort of use a reusable garbled circuit. There are other places to gain here.
So I'm just saying.
I can tell you in detail, perhaps offline.
I guess my question is, your framework, it looks like a very cool framework, and by plugging different randomizing codes,
Yes.
you get new results, you get like pre-derived fault,
Definitely.
you get new results. If you just plug different...
You get new results. You get new results. I don't think this thing was...
Now, from FHEs, you get a result that takes perhaps a lot of time to create, but at least it's succinct.
So I don't know how to do this from FHE alone without having an extra component. We can show that if you have FHE, you can sort of give up on the secrecy of the computation and use something like a message hiding encoding that only hides the message. We can discuss it further.
So I think there is a result that you haven't mentioned, right, about from Mohammed and others, I think, Moody, about impossibility in the random oracle model.
There's also a possibility in the random oracle model, right?
Yeah, I don't know exactly how it relates to this, or if it says something about the question whether you can do this from one-way functions, right? At least in a black box sense.
Okay, so in the random oracle model, there are some additional results. Actually, not full-fledged time lock puzzles. There are weaker forms of time lock puzzles. There are also some negative results that concern the random oracle model, and I think this is ideal notion. I'm not sure that we say anything about the plain model. But
maybe something in terms of black box reduction to one-way functions. You should think about that. So.
I'll think about it. It's a good point. Right. Okay, so just before I end, quickly mention two open things. One is really come up with other constructions of time lock puzzles. Our construction uses this strong object of succinct randomized encoding, which brings me to the next thing. How strong is this thing really is? Okay, and here, without spoiling the next talk, okay, I want to stress that something that seems to be quite crucial about these randomized encodings is whether they depend on the output of the computation or not. Okay, can you actually make the encoding smaller than the output of the computation? This turns out to be pretty crucial, and I want to note that here we don't need this. Okay, so we really need this this notion of randomized encodings. Okay, so this is all I wanted to say, I think. Thank you.